So we're looking at page 76 because here it's saying, you know what, we're not only going to want to sometimes switch the order of integration, but sometimes you're going to have to. And here I'm not telling you to do it because like I'm setting you up. Like it's not an instance where I'm saying, you know what, on the test, you better be ready. I could ask you to do it this way or that way. It's not really like that. It's really more so like, honestly, take a look at this innermost function. At first glance, it may look like something you can integrate. If you know how to integrate this, then by all means, go for it. E to the x squared. Right? If it were e to the 2 squared or e to the 2x or something like that, then I'd be all over it. You know, I'd say forget about switching the order of integration. I'm ready to go with this as is. But I can tell you that if that y came first, if it was integrate over the interval of whatever to whatever dy, it is a whole lot easier because then e to the x squared could be treated as a constant, right? So what I'm going to do here first is I'm just going to draw a quick diagram related to the base area, right? So, and really it's up to you how you want to go about doing that. Desmos might be the way to go. I mean, I'm kind of selling this Desmos stuff pretty hard. If you're not buying it, that's fine, but I think you might want to try to buy it, because not literally buy it. I don't want to screw with anybody's minds here. You know, like kind of pick up what I'm putting down. This the Desmos is a really good resource, and if you haven't figured that out yet, then you're probably going about things the wrong way. And I know because some people early on in the course wanted to go with tried and true TI-84 calculator, and that's all well and good, but between Desmos and GeoGebra, you get your 3D, and you're not limited to just single variable stuff. So, I mean, if you're not sold, then I don't know what to do for you. I'll keep trying though. All right. So when we look at the bounds here, it's very often glossed over and forgotten that those bounds are functions. All right. So, and it's all dependent on whatever the variable of integration is. So in this case, it's a dx, which means that I'm going from x equals y and Desmos understands that as y equals x is the same thing. I wrote x equals y, you know, because I'm writing it from right to left, but it really translates to y equals x, right? And 1 equals x or x equals 1, right? So I can just type it in just like that. So I'm looking at a base region that is triangular. All right, now what this is telling me is that the y values, all right, as indicated by this, are going from 0 to 1. One of the most powerful assets that's offered by GeoGebra and Desmos is the slider concept. It really makes a big difference, right? So if I say y equals some constant c, you know, y equals a, y equals c, whatever. I might have used c already for something else because I'm still kind of working off of the same Desmos here. Let me come up with a new. Weird. C. File, new, x equals 1, y equals x. And then let's say y equals a. It's so weird. That's not what I wanted to do. I created a slider here for the 1, which is fine if I wanted to move that, but I wanted a slider for a, and right after I sing the praises too, no less. Crazy. All right, so let's say, yeah, no, it's not asking me for a slider. All right, well, whatever. I'll just do it without the slider this time. Thanks a lot, Desmond. So let me know. All right. So I want to go from, oh, you know why? All right, I just figured it out. I'm so stupid. Right, so let me just type in y equals 0. Desmos didn't screw me up. I screwed myself up. Right, when you put in a constant function, so whether it's a horizontal or vertical line, it knows that sometimes that varies. And so it automatically makes it a slider, and I lost sight of that. I'm going from 0 to 1. I'll leave the step alone. This allows me to slide on up. All right. So what we would be doing here, based off of this scenario, based off of what they told us, is we would be creating little rectangles, little arbitrary rectangles going from y equals x to x equals 1, right? Which is kind of a weird thing to think about, but and really it's x equals y. That's an important distinction. So it's an x value equal to y going to an x value equal to 1, right? So those are vertical lines, right? So spanning from x equals y to x equals 1. And then from there, we're propagating upward, or we're propagating throughout the area based off of the opposing rectangles going from 0 to 1. So it's really going, if I can oversimplify, left to right, bottom to top, right? So let me get the diagram in here and I'll mark it up. Copy, done, save the photos. All right, so what it's doing is it's going, like I said, from left to right. So arbitrary rectangles, I'm going to give them infinitely thin width, which means I'm just basically drawing lines and hoping that you'll believe me when I say that they're really rectangles. Right? With thickness dx. Right, so for example, I just marked one of them as dx and try to keep it somewhat reasonable. So what it's going to do is it's going to collect all of those rectangular areas, add them together, and then and really when we're getting those rectangular areas, it's multiplied by multiplied by z equals e to the x squared. So it's giving you the height. So you got to imagine that this is a top-down view of the base region. So this is really, it's definitely rectangular, but you're looking at a distance corresponding with y equals x, right? So the height is y equals x in this context, multiplied by dx, and that gives you the thickness of the base rectangles, give it some height, and now you have a volume, right? So what we're saying, and then restrict that from a y value of 0 to 1, right? So I don't want to go any higher than 1. So when I draw my, because I really can stay between 0, x equals y and x equals 1 for x, but in terms of the length, I could keep going, so I need to have that extra restriction on the other end, right, to allow the thickness to only go so far, right? So what this is telling me to do, copy, is swap the boundaries of integration. Right, so instead of dx dy, it's going to be dy dx. It's still going to be e to the x squared, but I have to decide what my new boundaries of integration, shockingly I used the term correctly this time, right? So I need to decide what my new boundaries of integration are going to be, in order to allow for that to happen, right? So now, from the perspective of this, this variable y, right? So my line segments that I drew, those aren't going to be vertical anymore. They're going to be horizontal, right? Really hurts. So I'm going to start off at 0. All right, a little itch here. All right, so if I want to have that region, that correct region, I'm going to be looking at something like this. All right, the low bound. Oh, Christ, it's just not letting me work here. Oh, I see what happened. I already had a point there. That's why it went a little wonky on me. All right. So I want to be able to go from y equals 0, because if you're really just kind of thinking about this, we're looking at it from the perspective of the y-axis. The lowest value that I can have for y is 0. But in terms of y, the highest value I can have, you might think, is 1, but it's really related to the function itself, because I want to have that restriction in order, right? So we're going to go from y equals 0. I'll write it as 0 equals y to 0. I'm sorry, spring cramp, y equals x. So I'll write it as x equals y here, right? Because we're changing the perspective. We're going from y equals 0 to y equals x. But then I also want to have the restriction in terms of x going from 0 to 1. All right, the variable bounds of integration should always be the innermost integral, right? Now, when we learn about triple integrals, you're going to see that, you know, it's going to be more than just one integral that plays out for, right? But if you're going to have variable bounds of integration, it's going to play out that way, right? So again, just a quick recap. What we did was we had our arbitrary rectangles. In the original problem, it went from x equals y, so the line, the diagonal line, to x equals 1, right? And then we worked our way upward from y equals 0 to y equals 1. So we got all of our base cubes, or base rectangles, if you want to keep it more general. It's not really kind of locking in the way I want, but all the way up through that region until we accounted for everything. Probably better off just doing a freehand. All right. So then when we did it from the perspective of y, what we did was we started off with y equals 0 and went to y equals x, right, as the uppermost bound. And then we propagated outward, overused term of the day, from 0 to 1. All right, that allows us to find the antiderivative in terms of y, which is just simply e to the x squared y over the interval of 0 to x, because it's in terms of y. So I would say x e to the x squared minus 0 e to the x squared, so 0. And then we would integrate that over the interval of 0 to 1 with respect to x. Right now, at this point, it's up to you which way you want to go. If you wanted to do that by hand, it's not really that bad because it's just it's an easy use sub. But again, I've been pushing this whole Desmos thing, so why not, right? Let me just get rid of some of these. So function, integral, 0. I said 0, going to 1. Oh, poor quality 1, as in I put it in the wrong place. X e raised to the x squared power. That didn't put my parens in. I'm going to pay the price for that if I'm not careful. Dx. And so we get 0.859, which isn't really, you know, like, it's not a bad answer. Is it exact? No, because our real exact answer in this case, because exponential e would involve e in some capacity, but again, I'm not concerned with that. All right, so 859 units cubed. All right. And again, this is just looking at the base triangular region and all the cross sections that go along with it. That would be associated with the solid itself. It's a little bit trickier to visualize. If you only are concerned about the base region, that makes things a lot simpler. All right. But it is a matter of perspective, because it's very easy for this problem, for example, to think, well, I'm going from 0 to 1 for x, and then 0 to 1 for y. What's the big deal? Well, if you do that, that's going to give you a rectangular base region rather than a triangular base region. So that's a problem. And people would say, okay, well, so what? I'll just take my volume in half and cut it in half. Well, that would only work if it were a symmetrical figure. I don't know, you don't know what's going on above this in space. You know, it could be something where it's flat, like a plane, then in which case it'd be fine. But it could also be something that's kind of wonky, you know? So how do you know that the part that you're cutting in half is going to be equivalent for each region? You know, that's not going to play out, right? So you got to be really, really careful about stuff like that. So I'll put a star on the next one, because it's an expansion on something like this. You know what? Debating internal debate here. I'm thinking maybe I'm worried. You know what? I'll do it with you. It's only a case where you're writing an integral, so it's not going to be too crazy, but it's definitely worth taking the time to do, because people have struggled with this before. So write an iterated integral. That just means multiple integral. That can be used to compute the volume of the solid bounded by the surface and the 3 coordinate planes, and confirm your answer with the geometric formula. So basically, I'm looking for the first octant. First octant of a sphere. Right. So we know that that's just going to mean that we take the volume of the sphere formula and divide it by 8, and we'll have our answer. Right, because we have 8 congruent regions, so that's easy enough. At least we know how to verify our answer. Now the other part is to actually come up with the answer. All right, so let me give you a quick sketch, and by quick sketch I mean let Desmos do it. X squared plus y squared equals 1 is going to be the base region for the whole shebang, and that's because if I square both sides, I get z squared is equal to 1 minus x squared minus y squared. Add the x squared to x squared plus y squared, x squared and y squared to both sides. I get x squared plus y squared plus z squared is equal to 1. All right. So how does that help me know that it's going to be a circle? Well, this is the unit sphere. All right. On the xy plane, z is equal to 0. Therefore, you would get x squared plus y squared equals 1, which would be the unit circle. All right. So that's where that information is coming from. Oftentimes, you could just do it based off of sight recognition. Now that you're familiar with what a sphere looks like, and specifically the unit sphere looks like in when it's solved for z, you know, just change the coefficient. Let's say it's 4 minus x squared minus y squared. Then you know it's going to have a radius of 2. because it's just the square root of whatever that coefficient is. So anyway, we have this. Now what I would need to do is establish what that would look like in the first quadrant here, octant for the sphere itself, right? So what I would do is, I could do it a couple of ways, but we could find the area under the curve going from 0 to 1 in both directions. But what I'll do is I'll just do a quick sketch, right? Because Desmos can handle a lot of that. If you tell it what to do in the right way, it can pretty much do whatever you want it to do. But I'm just going to kind of keep it simple for now. Save it to photos so I have it later. All right, so what I'm concerned with again is that, like I said, the first octant. All right, so let me see. This would be somewhat geometry tool. This would be somewhat shocking if this actually worked out the way that I wanted it to. Nah, of course it doesn't. But that's what I was going for. That first, the first region there, the first octant. All right, so if I create my arbitrary rectangles going in the y direction, all right. So if I decide I want to go with respect to y, then my second integration variable would have to be with respect to x, and those would be the ones that would be constant, right? I can go in either order. I just have to come up with the function that would best or be most suitable for that, right? So I'm just going to make a decision. I'm just going to decide right now that we know it's going to be a double integral, but I want to have my function again, z, which is the radical 1 minus x squared minus y squared. I'm going to do it with respect to x first. You know what? I'll do it with respect to y first. All right, which means that these bounds, this one and this one, have to be in the form of y equals. All right, because that's where my change is. It's in the form of y equals. All right, so it's a question of y equals what to y equals what. Well, let me just diagram it out. We're talking about going in this direction. So we'd be starting at 0, and I could say I'm going to 1, but that's constant, right? If I say I'm going to 1, I'm saying that I'm going all the way up to here. That's rectangular. What I want to do is go up to 1, yeah, eventually, but I want to be bounded by the curve's circumference. All right, now that is in the form of x squared plus y squared equals 1, but if it's going to be solved for y, all right, and it's got to be solved for y specifically so that it just gives us that piece, it would be y equals the square root of 1 minus x squared. And we can verify that. All right, that's going to give me the top half of the circle. Now I would restrict that, which I'll get to in a second, but that's what we're looking at here. Right, so I want my my y values to go from 0. If I can get rid of the little stray mark there. I want it to go from 0 to the square root of 1 minus x squared. So let me just smidge this over here real quick. All right, now if I want to keep from actually covering everything between -1 to 1, what I would do is I would restrict this so that it only goes from 0 to 1. All right, because again, it would give me the whole shebang here. It would give me from -1 to 1 unless I make this restriction. And so now I'm stopping it at this boundary, right? So we're going all the way over and through, and we're now restricted to just that first octant of 0 to 1. All right, now in terms of actually integrating this, it's not impossible. Oh, I need a dx here, apologies. It's not impossible. We can get it, but we don't want to. All right. And that might be the understatement of the year. Like, yeah, we don't want to do work. Surprise. You know, that's not news to anyone. There's an easier way to do it, because when you're dealing with circular functions, we have a coordinate system that works specifically for circular functions. It's the polar coordinate system. Right? So we're going to explore that now, and you'll see how that's going to make something like this a whole lot easier. All right, so let me stop this recording.